the projective space. So we have constructed the sphere and the projective space independently, and then we finished last lecture by observing that actually there was essentially a way to pass from one to the other just by thinking of the antipodal map as an equivalence relationship, inducing an equivalence relationship on the sphere. And in some sense, the quotient structure of the sphere would give rise to the same structure as the projective space. Now, this is a completely general phenomenon. So this is the simplest examples of what are called discontinuous actions. So let me spend a few minutes just giving you, and actually even discontinuous actions are a very intermediate step. I mean, one would like to play the game I'm going to describe to you also with non-discontinuous actions up to a certain point. Okay, so remember, so you should have in mind the example of the sphere with the group Z2. Z2 is the group acting by associating the point and the antipodal point, okay? Putting together the point, one point with its antipodal point. So what is the general picture behind this? Is that if you say that a group G acts on M if there exists a map, let me call it phi, from which takes an element of the group and the point of your space and associates another point of your space. So so here many notations, many equivalence notation will take an element of the group that we call little g and the point, and it gives me something that I will denote by g dot p, and actually if I fix G, then of course I have a map phi from M to M, but actually with G fixed, so I will indicate with the lower G here, which takes P and gives me G dot P. So the action of one single element, okay? So these are all notations that I will use. So I need a map such that with few properties. So one, for any G, phi G is a diffeomorphism. Now here, just because I'm doing differential geometry, otherwise you can change your, I mean, if this was just a topological space, you could actually say it's an homeomorphism or something like that. I mean, here at the level we are doing. And also, of course, in every group there is a special element. So if G is equal to the identity, now this is called, I will denote by E, the identity of the group. Then I also require that phi E, so if I take the identity element of the group, actually nothing is happening. Okay, so the action of the identity is nothing. Okay? But then I want some kind of compatibility between the algebraic structure of the group and these actions. So what I really require is that for any G1, G2, in G, phi, you see, I can look at phi of G1 dot G2, don't be confused. I mean, I will also denote by dot the product in the group. Okay, so this is the action of this element of the group. But I can, of course, I can compare it with the composition, and I want them to be the same. Okay, so that if I first act with G2 and then with G1, it's the same thing as acting as G1 times G2. Okay. Okay. Now, so this is just a group action. Now, I will say that the group action is called properly discontinuous. Kind of a strange name, but you will realize that it's actually a good name. Properly discontinuous if for any P in M there exists UP contained in M open of course, by this notation, I always mean that it's a neighbor of the point P. So there exists an open set containing this point, such that the group moves this open set into something completely disjoint. So if I take UP intersect G times UP, I get the empty set, of course, except for the trivial case, because of course I required G to be nothing. So for any G different from the identity. Okay, of course, for the identity, UP and GUP is the same thing. Okay, so really what we have to think is that for any non-trivial element of the group, there are at least, and you have to think, of course, that these open sets should be quite small open sets containing a point which are moved completely away from the original point. Okay. As I said, of course, the prototype situation is this antipodal action of Z2, for example, on the sphere. Now, you can imagine on the sphere, you take a point, and since this point is moved, well, so Z2 has two elements, 0 and 1, I mean, depends on how you, so 1 and minus 1, let's say. Okay, so 1 does nothing. Minus 1 moves it a lot, that's the point, it's moving a lot. So that means certainly there is an open set containing a point whose antipodal mirror doesn't touch it. Okay, so they are very well separated. Okay, this is the idea. So of course, a group action induces an equivalence relationship. So of course, we say that P1 is equivalent to P2 if there exists an element of the group P1 is equal to GP2, okay, if there is an element of the group which takes one onto the other, I mean, it's obvious that this is an equivalence relationship under these conditions. So then we have a map, we have a quotient map. So this equivalence relationship, instead of denoting by the usual symbol, we just denote it by the group itself, okay? That's the standard notation. Okay, so this is the quotient map. Even though, be a bit careful about this notation, because the same group can have many different actions. So this seems to indicate that this object depends only on M and G, which is not true. This depends on M, G, and the way G acts. Okay, so it's a little bit delicate, okay? Now, the point is, all this, essentially, I mean, besides the word diffeomorphism, belongs to the word of topology, but the point is, as we did for the sphere and the projective space, the interesting observation here is to prove that if M is a differentiable manifold, the quotient has a natural differentiable structure. Okay, so and of course, if the group acts properly discontinuously, then has a natural, of course we will call it the quotient or the induced structure. Well, I just start the proof because then it's just a sequence of check. So the point is, of course, you have to repeatedly use the definition of properly discontinuous. Okay, so how do I construct charts in the quotients? Okay, that's the point. Starting from charts on M. Okay, now the point is, for any P in M, if I let me first work upstairs, okay, so I have M mapping to M quotient G. So I start working a little bit before, I prepare everything on M, and then I will just quotient everything down. So on M, of course, for any P there is a chart. This is, I know, this is something I know because it's a manifold. But the point is, I can certainly construct some kind of, let me call it just like this, X of V contained in U contained in M. Okay, so this means a chart XV which maps onto an open set U of M. But of course, by restricting everything by continuity and homeomorphism property of the charts, I can certainly prescribe this U here to be one of these these open sets here. Okay, so the ones which are moved nicely. Okay, by restricting V sufficiently. Okay, so I can assume U has the property that GU intersects U is equal to 1 for any G different from the identity. Okay. Okay. So once you understand that this is what you have to do, everything becomes kind of a very simple check. Because now, so what do you do? Why of course now everything becomes easy? Because if I look at pi restricted to U, you see, pi restricted to U is essentially the identity. Because there are no other, inside U, there is nothing else equivalent to each other. Okay? So, I cannot really say the identity because the spaces are different. I mean, I cannot say pi of P is equal to P. This is a kind of an equivalence relationship, but that's the model. I mean, pi identifies U and the quotient of U. Okay, these are completely indistinguishable at this point. And so, which should be my chart? The charts on the quotient will be just the same open set. So now if V was sufficiently small in order to achieve this, I won't touch it as a domain in Rn. But then of course the map will be different, but the map will be just not to make a mistake. So X goes from V to M, and then here, so I have to take pi composed X. Okay. So this form, these are charts for M quotient. Okay. Okay, I leave you this as an exercise. What is the only non-trivial thing? Well, of course, what do you need to prove? That they cover, but okay, they cover, it's obvious, because I started from any P, U, of course, was, U was containing P. So, if U contains P, of course, these objects here will contain any equivalence class. So, covers is okay. So, the only thing you need to check is that anytime two things overlap, the change of chart is differential. And you can imagine, actually always go back to the case of the sphere and the projective space. What's really going on? Okay. Just try to write down what do you have to prove, and then you will realize it's automatic. Okay. Of course, you will need this. Okay. Basically, the idea is that every time two charts on the quotient overlap, of course, you would like to lift them to the original space. But of course, when you lift from a quotient, you cannot say that the lifts overlaps. The lifts will be related by an element of the group. Okay? So it's not that you go upstairs and you find two things which overlap. See, once you realize that this is the key, okay? You take two things overlapping on the quotient don't mean that pi inverse overlap in M. But they will be related by an element of the group. Since they were equivalent downstairs, there must be an element of the group upstairs which takes the inverse image of one open to the inverse image of the other, at least on the intersection. Okay? And the point is that this map is a diffeomorphism. Because it's true for any element of the group, so in particular for this element of the group that you have found. Okay, so this is kind of a general picture. Just to, we saw as an example the sphere and the projective space, but there is certainly another very famous, in fact, probably the first case, which also explains a little bit this name of properly discontinuous. You see, properly discontinuous, I mean, this is just a psychological thing. I remember being a bit disturbed when I was a student. I found this notion. I said, but what does it mean? This is the most beautiful thing, and you call it with the most horrible name, essentially. I mean, you are saying, this is the most horrible action, and you say, this is great, because we can do many things. But actually, so what you really have to think is that, yes, it hints to horrible property, but actually it's a very nice property, the idea that you separate open sets with the action, okay? So in particular, if the group is discrete, you expect to be able to do this. Like Z2, because, okay, if every element, if the group is made of a finite number of a discrete number of things, then, okay, you expect, nothing is a theorem, and in fact nothing is exactly true, okay, to be able to separate things. But of course, groups could have families, could have continuous families inside the group. Take the orthogonal group, GLN, whatever. I mean, all these groups, of course, they have continuous families inside. So of course, if you can move continuously in the group, you should imagine, suppose there is a curve of elements. Suppose you can actually take a family parameterized by some real numbers of elements GT, okay? So how can you separate open sets? You would expect, for example, this map to be continuous, no? Well, that's actually the nightmare situation. You say, well, this is beautiful. No, this is the nightmare situation if this contains a continuous family of elements. Because, of course, by continuity, you cannot separate things. So this is actually hinting to the fact, okay, even if it contains families, it has to jump. It has to be a really horrible action, okay? That's why, in some sense. So for discrete groups, it works quite well. For continuous groups, it's a mess. It's a nightmare, okay? So just to finish this thing, because we will not come back to. So of course, as I said, example one was a SEN quotient Z2, which was given RPN. So now let's look for a second example, because it's nice, and it's probably the most famous one. So again, take Rn, or take Rk, okay, the standard as a manifold, okay, with the standard structure. And now, of course, look at Z to the k. This time the k is upstairs, it's not downstairs. So translations, so choices of k integral numbers. Okay. So what do I mean by, and now how does this thing act on this? Well, it acts in many ways. The simplest is, of course, this one. So you take an element of the group. I need to tell you what is G times P. So I need to define this. So let me take M1, Mk, and of course by this I will mean an integral vector, no? An element here, acts on a real vector by translations, okay? So, of course, there is not enough by M1 plus x1 and k plus xk. Okay. Okay, so this, I think you have seen it many times, written in a different form maybe, but this is always the same thing. So for example, what is, for k is equal to 1, what's going on? It's R, and of course, since I'm going to identify, no, I want to, first of all, is it properly discontinuous? Well, what is this asking? Take any point of Rk. Can you find an open subset of Rk which is translated into something which does not intersect the original open set? Well, of course the answer is yes, as long, for example, pick a ball of radius sufficiently small. Okay? And then this is, for sure, it's translated somewhere which does not intersect the original ball. Okay? And this, of course, all depends on the fact that these are forced to be integral. Okay? If here I would put something more complicated, then this will not be true. So by the general picture, this object here is a manifold. And in fact, you know which manifold is it. It's called the torus. And so it's usually denoted by this. Okay? Because in dimension 1 it's the circle, it's a swan. Okay? The usual topology. I think you have seen it many times in many different forms. Okay. Okay. Yeah, I think this closes this part of the story. So now let's move to the general theory. I didn't say explicitly another source of, I mean, this gives a big, actually, quite big source of examples of manifolds. Other sources of examples come from variations of, trivial variations from something we did for surfaces. For example, everything which was coming down from the implicit function theorem. The implicit function theorem has nothing to do with R2. It works in Rn. So for example, if you take a map from Rn to Rk, and you take a regular value, the inverse image of a regular value will be a differentiable manifold of the right dimension. But that's just the implicit function theorem. Okay, there is nothing new. So of course, all these theorems will pass to manifolds, because these will be automatically manifolds which are subsets of Rn. Okay, so there is nothing new from surfaces to what we are doing now. So I won't waste time on that. So now we need to analyze a bit better the structure of the space of tangent vectors. Okay, so remember, it took us this time a little bit of effort to define tangent vectors. And now it's very important and convenient also technically to define a new object. In fact, out of tangent vectors we can define a new manifold. Okay. Which actually belongs to, again, another big family of manifolds. So, what does it mean? The tangent bundle is an English word which just means put everything together. Okay, so what does it mean in this context to speak about bundles? Is that actually we define, of course, M is smooth. We spent a few minutes about discussing what is this. Okay, if you fix a point, we know what is the tangent space at this point to the manifold. So now let's put everything together and let's give it a name. So I will call Tm without any index. Okay, so the tangent bundle as a set is just the set of pairs PV, where P is a point of the manifold, and V is a tangent vector at this point. Okay, so there is a relationship between P and V, which is hidden in the fact that V is a tangent vector at P. Okay. Now, the point is, this object, this is just a set. This set is, in a natural way, a manifold, a differentiable manifold, starting, of course, from a differentiable manifold. So how? And this is not just an example. This is very useful for many reasons. The idea is to construct charts. Actually, this is called the tangent bundle, okay? The idea is, of course, to construct charts for these objects out of charts of M. So start with our famous U alpha X alpha atlas of charts for M, okay, where alpha will move in some family of indices, okay? Okay. Now, associated to this, remember what we spent time on when we discussed the tangent spaces, that every time, it is true, it is still true what was true for surfaces. Every time we choose a chart, we have a canonical basis of the tangent space at every point. Okay, it's just that this time we have to give the right interpretation to the tangent vectors, but this was still true. So remember, for surface it was xu, xv, now is this famous vectors ddxi. Okay, now, since I have many, I have to be a bit more careful about this choice of indices. So, a chart, of course, I can think of the charts as a family of maps. Okay, so let xi alpha be the coordinate functions for one choice of this, so for U alpha X alpha. Okay? So these are the maps, these are the coordinates over the Rn where this object lives. Okay? So I goes from 1, let's say M is of dimension n, so I goes from 1 to n. Okay? So for any point in X alpha of U alpha, so for any point touched by this chart, I know, we have argued, that the family of vectors ddxi alphas, okay, form, of course, at the point Q, form a basis for TQM. Okay. Okay, so how do I define charts for the whole tangent bundle? So define, I won't touch the set U alpha, but I will call it Y alpha, a map from U alpha cross Rn. So this will be my new domain of a chart. So in fact, if I'm writing this, I'm already telling you which will be the dimension of this. Because this lives inside Rn, and this is another Rn. So this will be, if I'm right, believe me for a second, this will be a 2n dimensional manifold. You double the dimension, okay, of the original manifold. By doing what? How do I construct this map? So this will take a point here, which is given by x1 alpha, xn alpha. And here I'm just taking any bunch of numbers, an n-tuple of numbers. So how do I want to call it? U1 and Un. So out of this, I need to construct what? A point and the tangent vector to that point. Well, the point is quite obvious. I mean, I have these coordinates here. I map with x. on M. So the first part, no, I have to give you a point and a vector. So the point is clear. I'm just giving you x alpha of x1, xn. And the vector, well, these coordinates I told you give me a basis. Now I have numbers, okay, I take the linear combination with these coefficients of these vectors. So here I just take sum over I from 1 to n of ui dx alpha I. At which point? At this point. Okay. Okay. Okay, so this is okay because up to now this is nothing, this is just a set. So the only thing I need to check is that this path goes from this place to this place, and this is for sure true by construction. Now, so now the claim is that, of course, if I put everything together, so I first write u alpha, first the set, so u alpha cross Rn, comma y alpha is an atlas of charts. Well, defines a differentiable structure. On this set here. Okay. So what do I have to check? Well, the first thing is that, of course, they cover, so the union over all the chart, of all these candidate charts. So, of course, here the set of indices will range in the same space as before. Okay, for any alpha as before, I have a new thing. So first I need to prove that they cover everything. Well, but this was true here at the P level. No? M is covered because this was an atlas of charts. Okay? And now the vector part, well, but this is okay too because I'm taking any number. I mean, we argued that this was a basis. By being a basis, if I take any possible linear combination, I take the whole vector space. Okay? And since I don't put any restriction here, this will be any vector. Any vector has to be of this form. Okay? So this is actually equal to Tm by default. I mean, essentially we have already proved it. It's all, the only delicacy is in this sentence here. But that's what we proved last time, I think. Okay? Okay, now we have the most delicate one, the transition of charts every time two things overlap. So let's go into this a bit more in detail. So now let's suppose that we have alpha and beta such that something is in the intersection. So I pick P and V, which lies actually in the section of y alpha of u alpha cross Rn, intersect y beta of u beta cross Rn. Okay, so suppose there is actually something in this intersection. Okay, actually it would be very convenient to rewrite this object here. Formula will be dramatically simpler. If I just observe what? That actually I can write this object here as dx alpha at the vector u1, un. So dx will go from where to where? X goes from u alpha, which is a subset of Rn, to m. So dx goes from the tangent space to Rn, which is Rn, to the tangent space of m. Okay. this is actually, I'm rephrasing something we said here. So when I said what is the vector ddx1, I mean, now suppose, for example, there is no alpha, okay? So we have one chart, and I'm saying, what is ddx? What is this symbol? ddx1 is actually dx of the vector 1, 0, 0, 0. So that's the partial derivative in the first direction. Remember all this interpretation. I'm just writing the mathematical formula. I'm not telling you anything new. Okay? So what is this? This is dx alpha of the vector, in short, okay, of the vector u, which has these components. Okay, this makes the formula a little bit shorter, because if I have a point in the intersection, it means that this PV is actually, I have two forms of writing it. So this will be x alpha of some q alpha, if you want, dx alpha via u alpha. Okay. You see, I'm just writing the fact that PV is in the image of this map. So the first part is x alpha of something, and the second part is dx alpha of something. But it's also in the beta. So this is also x beta of q beta, dx beta u beta. Okay, note that the objects are all different. I mean, Q alpha, Q beta, I mean, they all live in different spaces, so. Okay, and what do we have to, okay, this is general fact, but what do we have to write in order to check that the change of charts, so if I take the gray area, remember in the picture that we stopped doing. Now these two things intersect, there is a gray area, so that means there is a transition between the gray area inside U alpha and the gray area inside U beta, of these two things. And the transition is of course given by what? Y beta inverse composed Y alpha, or vice versa. Okay, in one of the two ways. So, what is, basically, this means I have to write this, okay, where it makes sense, the gray area, the famous gray area, okay. And in the gray area there is what? There are exactly these objects here, the alpha, I decided that I'm starting from alpha and then going to beta, okay, so this takes Q alpha, U alpha, okay, and gives me something. Okay, it's written here what it gives me. I mean, one step I just copied. This is Y beta inverse of X alpha, Q alpha, dx alpha, U alpha. Okay? Now, this is just copying the line above. But now this is what? Well, how does y act? Well, acts like x on the first part and something and dx on the second part. So on the first part, this gives me x beta inverse composed x alpha applied to q alpha. And in the other part, it acts like, well, y acts like dx. So y inverse acts like dx inverse. So this is dx beta inverse of dx alpha u alpha. Okay. And so we are done. Why? What do I have to prove? That this is a differentiable map. Okay, the first part is differentiable because X must satisfy this property because X was a chart, was a system of charts. And then, also, of course, if X satisfies all these properties, in particular it's differentiable, well, also this one has to be differentiable, okay? Okay. Very good. So this ends this example. And you see, now, from now on, actually, this tells us also a little bit, this is again a bit psychology, but you remember we have always viewed something, in our case a surface, a point and a tangent space like this. But you see, the problem, of course, was that if you move the point and you think that you are living inside R3, these planes intersect. We never actually cared. No, we drew like that, and only our intuition. But you see, the picture starts being very bad. Because you have these planes which move around and they start intersecting in R3 in very strange ways. We never studied actually how. Okay. Now, I'm just telling you, so suppose now this is your manifold M. How do you, I suggest you to think of the tangent bundle or whatever bundle. You see, the tangent space at the point P and the tangent space at the point Q are completely different in the abstract picture, which is the right one. I mean, it doesn't even make sense to say there is a vector which is in the tangent space at P and in the tangent space at Q. Because these are abstract vector spaces that are not subspaces of anything. These are completely disjoint. Okay? So actually, the way you draw the tangent space from now on, I strongly recommend is this. So this is actually the tangent space at this point. Because it's much more important not to be, the fact that you want to think of the best linear approximation is actually an accident. It's much more important that you don't mix the different tangent spaces at different points. Okay, this is just, because actually you will see them in books, this kind of thing. You say, come on, this is the tangent line, and you think everybody went crazy completely. Okay, but actually it's right. It's the right thing to, it's the right picture to have in mind. Okay. You see, the other picture is really a Euclidean picture. It's really due to the fact that this lives in Euclidean space, which is something we want to stop forever. Okay. Okay, so this actually, as I said, this belongs to a big family of objects, I mean bundles in general, which are very useful. I think we will stick to the tangent bundle. Maybe we will do the dual one in the last lecture, possibly, which is called the cotangent bundle. Now, let's spend another few minutes on the structure of the space of vectors, of tangent vectors. So, now, first of all, so what is a vector field? That's the basic question. Now, actually, thanks to the fact that we spent 10 minutes on defining the tangent bundle, there is a cheap answer to that. Because remember in Rn, again, this is a point that in R3 was very simple. You take what was a vector field in Rn? What was a smooth map from some domain to R3. And then you say, well, so the smoothness part, we solved it by saying it's a smooth map in R3. And then you say, okay, and then for every point it has to lie in the tangent space to the surface. And now on a manifold, how do I say it's smooth? Okay, so now I know what it means to stay on the tangent space at every point. But what does it mean it's smooth? Well, that's exactly why we spent 10 minutes on the tangent bundle, because I can say a vector field let's say X. Well, now notations are getting, but actually vector fields are usually called X, Y, and Z. Don't be confused with the charts. Okay? So a vector field is on M. Well, one line, now I can tell you, is a smooth map X from M to Tm. So you see now, this is a differentiable manifold, and now I spent 10 minutes, and this is a differentiable manifold. So now I know what it means to be a smooth map between these two things. So in one shot, I can tell you it's a smooth map here, then there is only one thing missing. A smooth map from a manifold to its tangent bundle, of course, takes a point P, and a priori can give me a pair QV. So you see, it's not written anywhere here what I need, such that X of P is actually a tangent vector at P. No? A smooth map could actually change the base point of the tangent vector. Okay. Very good. So, locally, if I have a chart, which now it's going to be interesting, because if Ux is a chart, how do I write X? X now is the vector field 2. Okay? So X of P, well, at every point has to be a linear combination of the elements of the basis which are induced by the chart. So this has to be, for some choices of coefficients which depends on P, something like this. And now it's easy to check, but it's important to realize that the structure of differentiable manifold that we have just defined on the tangent bundle is the one which makes true the obvious claim. A vector field is smooth if and only if the coefficients are smooth functions. Okay? So locally it's something like this. It's just a linear combination with smooth coefficients in the old-fashioned way, because now these are real numbers. Okay? And remember that the new kind of right interpretation of a tangent vector of being something which takes functions and gives the derivative of the function in one direction. Okay? So remember, X is actually point by point is a linear operator. Okay? So X will take a function and will give me something, will give me another function, but that I can evaluate at the point P. Okay? Take this formula. So this is actually the sum. Locally, it will look like this. Remember that this is an operator now, huh? Because that's the only thing I have. So it's something which takes a function and gives me the derivative of this function in this direction. Okay? So remember, vector fields acts on functions and gives me functions. Okay? So in some sense, you can also say the smoothness of the vector fields is also the fact that it's something which takes smooth functions to smooth functions. Okay, that's an equivalent way to rephrase it. Okay, now, many of the interesting things coming from vector fields come from the following observation. Question. Pick f a smooth function. Okay? So what I just said is that if I take a vector field, I can act on the function and I get another function. So in principle, I can repeat it. So if I have two vector fields, I can look at x of y of f. So very natural thing, which is kind of reminiscent of the Schwarz lemma or something like that. I think we called it the Schwarz theorem. I mean, the commutativity of the partial derivatives, in some sense. So is this y of x of f? Is it the same thing? Well, this is non-obvious. Let's see what they are. But I don't expect you to see the answer. Okay. Let's see. Notations. X is this, I've already written, but then also y. Let me invent a name for the coefficients of y. Again, this will be locally, let's say, bj ddxj. Okay? Now, so y of f. So what I'm doing is what? Is the sum. All the sums will be from 1 to n, so I don't write where. Sum of ai times d dxi. I'm writing x, but this acts on what? On the sum over j of bj df dxj. Do you agree that this is the left-hand side of what I wrote? No? I just replaced the local expression. So let's do it. After all, now I know that these are actually the old-fashioned partial derivatives. When I see them acting on a function, this is the partial derivative on this function. So how much is this? Well, this is the sum over I of ai. And now that's the only thing you have to be careful. But that's the crucial thing. These are functions. They depend on p. Okay? So the derivative does something here. Let's see. So this gives me sum over I, sum over j of dbj dxi df dxj plus bj second derivative of f dxi dxj. Okay. So far, so good. And I'm not saying that this is the answer, unless you are particularly quick. It's too early in the morning to be particularly quick. So let's do the other one, and let's see if we get the same result. Okay, so this was left-hand side. Let's do right-hand side. So y of x of f. Well, but now let me skip because I can take this formula. It's just I'm switching a and b. Okay, so let me write down directly the answer. So the answer is what? Is the sum over bi of the sum. This is sum over I, sum over j, the partial derivative of aj dxi df dxj plus aj second derivative of f dxi dxj. So are they the same? No. Of course, there is a one part which is nice, because of course if I take ai bj second derivative, well, here's just bj, ij, and then it's summed over everything, so plus the fact that of course the calculus theorem, okay? The commutativity here, it's obvious, is the old theorem. So this part would be okay. But there is this part, and of course, in general, there is no way that, what is it? bj, bi. Well, bi. Let me first, aj. Compared to ai okay, there's absolutely no way, because this has to be true for any f. I mean, if two things are the same, it means they act in the same way on every function. Okay. But mind you, of course, there are choices of x and f for which this, for x and y, for which this is true. But not for any choice of x and y. For example, if for some reason a and b are constants, but this term disappears. Okay, but this is an accident, it's not a general function. Okay. Now, given this problem, there is also the solution in front of us. Because, okay, so this means that as a vector field, xf minus yx in general is different from 0, in general. Eh? But what it is? Well, we wrote it. Okay? The difference now in this way, it's what? It's the AI, it's this minus this. It's this minus this. Okay, so this would be, what I wrote here is exactly what? Is xy minus yx of f. Okay? But what kind of object is it? The point is, this is again acting on a function like a strange derivative. I mean, the action over function here is just d dx, sum with coefficients. Okay? So that actually means that, okay, this is non-zero, but it's still a vector field. You see what I mean? Is that I can take this formula and define it, now it's a longer equality here, like z of f. You need to check that this is a vector, no? The tangent vector. But you see, this acts in the right way, you know, on functions. So it's a vector. Okay, so let's give it a name. This is called the Lie bracket. Okay, so definition. And you denote it by this. Okay, so given two vector fields, I produced a machine which gives me another vector field. Okay? So it looks like a product. We are constructing a product in the space of vector fields. And that's exactly what we like. And this product, so this product has many interesting properties. Let them list here the most famous ones. Is somehow measuring the failure, remember, of this kind of commutativity of the partial derivatives on a manifold, okay, with respect to, even though it's not exactly a manifold problem here, because, well, not just, I mean, it's a kind of a subtle thing, because it really depends on, even in Rn, where the calculus theorem is true, you know how to, now you know what you have to do to produce two vector fields in Rn whose bracket is non-zero. So the fact that there are vector fields for which the bracket is non-zero is not the failure of the general theorem about the commutativity of the partial derivative. It's the special situation of those two vector fields. So those two vector fields do not commute when you see them acting on functions. Okay? So you have to be a bit more careful. So which kind of properties have this product here? Well, the obvious one is that actually, if you reverse the order, you get the minus sign. That's completely obvious. Another obvious thing, you see, I'm leaving the formula here of the local expression. if you take real numbers and you substitute a linear combination in one of the slots, of course if it holds for one, it will hold for the other via the property 1. You see, if this means what? That I have two types of coefficients. No? X1 is actually, was this coefficient here. So this coefficient becomes a linear combination of lambda and mi and other coefficients. If I replace in the final formula, what is the effect of taking a linear, instead of AI or AJ, I put a linear combination with constant coefficients. Why constant coefficients? Because here I'm taking the derivative. So also everything here is linear, and so this is linear. So that's the point. If these were functions, this was not true. I can multiply a vector field by a function, but then the nice property will fail. Okay? Then there is a slightly more mysterious one, which is okay. So if you take the possible permutation of pushing, no, I always push to by 1. X, Y, Z, X, Y, Z, X, Y, Z. No? And I do all the sum, I get 0. This is always called the Jacobi. Every time you have a product, somewhere you have a product which satisfies something like this is called the Jacobi identity. And then finally, sooner or later we have to worry about what worry. We want to know what does it happen when this was not a constant. So when this is not a constant, so now f, if f is a C infinity function, then what do you get if you do this? Well, it's written here again, the answer. So this term, of course, gets multiplied by f. So here there is nothing interesting going on. I mean, this will contribute to the, I mean, the obvious guess is this. But let's see, is this the whole part, the whole story? So, okay, this term here plays in this direction. It's part of the two things I would get from there. When I put it f times a here, of course, when I differentiate a and I put f outside, it gives me the other piece missing. And so that part is okay. But then I had an extra term. I have a df, so I have an a, b, df, dxi, df, dxj. Now f now it's a bit unfortunate as a name, because this was the action of already something. So this means I have to correct with what? I have to take it away, so in fact, or it comes with a minus. So the truth is, it's this one minus y of f x. Okay? Because at that point, what is left is a goes out here. Okay, it's easy. I think I can just complicate your life by saying something. Okay? Okay, so these are, of course, if you want to know what is the action over the second thing, you play the game with I mean, if you want to know what's going on with a function on the second. Okay, very good. So this gives a very nice algebraic structure to the space of vector fields over a manifold. Okay, and we will see it in the final lectures. How we can use it. And now in the last 12 minutes, I think I can just tell you about another technical thing. Have you ever heard of what is a partition of unity? Because now we stop. Now we freeze everything for a moment, but before passing to remind you, have you ever heard what is a partition of unity? Okay, so I need to spend 10 minutes. It's actually a quite useful thing. So this has absolutely nothing to do with what we spoke up to now. I just need to introduce you a tool. So first of all, in fact, for most of it, we can even speak about the topological spaces. So, okay, let me remind you. What is a locally of course, when you take a topological space, you take a covering. And of course, we are thinking of our charts, even though soon there will be also something else. And of course, you have spent a few months of your life studying the problem of whether you can extract out of a covering a finite covering. Because that's compactness, okay? Now, but in general, of course, few spaces are compact. So there is something in between, so locally finite. What does it mean that you can, well, in fact, you don't even have to apply to an atlas. So a collection of subsets of a topological space at this moment, okay? So of M, but now here you don't really need the whole structure of a map. Okay? It's called locally finite. If it is locally finite. I mean, sorry, sometimes the words are well chosen. So what does it mean it's locally finite? That for any point, only a finite number of them contains this point. Okay? If for any P in M, and in fact I should have given names to this collection of subsets. Let me call them U alpha. Okay, with alpha in some family of indices. For any P, there exists a finite number. A finite number of U alpha contained. Okay? So of course, if you have a finite number of objects, it's locally finite. So the point is that in general, this will be an infinite collection of things, but only a finite number of them will touch a given point. Okay? Okay, I don't have to tell you what is a refinement of something. And now, so there is a topological lemma in all the story I'm going to tell you that I'm not going to prove. So topological lemma, if you want to, it's actually not completely obvious. Any open covering of a manifold M as a countable locally finite refinement. And now I give names. So UI, XI. So these are charts. Now I'm assuming this is a manifold. Okay, so these are very special families of coverings, the ones given by charts, and such that XI. So such that UI, you can think actually, you can pick UI is a domain of Rn. So let's say we decide that UI is always a ball. It's the ball of center, the origin, and radius 3. Okay? So this is the ball. Ball, center, radius, okay? And xi of the ball of center, the origin, and radius 1 is still a covering. Okay, this is just the technique and nothing. I mean, here, actually, the delicate part is here. I mean, don't worry about these balls and this radius. I mean, once you get the property you want, you can always restrict yourself. Now, suppose that, for example, your domain of your chart was actually something like this, and then the origin is here. So, of course, you can construct immediately another chart with the property that you want, like translations. I mean, if you compose a chart with a translation in Rn, it remains a chart. So the fact that the origin is there is no problem. But you say, but maybe I have to translate here. Now here the ball of radius 1 is this and the ball of radius 3 is this. So I cannot, because maybe this was my u, and there's nothing I can do. But no, because I can enlarge. If I take an homothéty of Rn, if I have a chart and I multiply or divide by a real number, it remains a chart. You see, the size of this domain is absolutely irrelevant. Okay, you multiply by 1,000, and then the ball of radius whatever will stay inside here. Okay. So this is useful for later, but it's not the heart of the problem. The heart of the problem is to get to this point. Okay. So I want to have charts. Of course, xi of ui must cover. This is in the definition of chart. But I want everything to be covered, even if I take a slightly smaller thing. Okay? Okay. So we will call, on a manifold, we call this type of coverings by charts, we will call regular covering. Okay, so these things, once you achieve these properties, ui, xi is called a regular covering. Of M. Okay. I won't prove it because it's purely topology, not completely trivial. But now what do we do with it? So the only thing, actually maybe a picture can help. So now we are in the situation where our manifold is covered by these images of the balls of radius 3, but also the ball of radius 1. So there are some kind of larger sets and smaller sets. So this would be the image of the ball of radius 3. Let me just call it like this on the picture. And this would be the image of the ball of radius 1. Okay? And I know that just these ones, as I moves, cover everything. And the thing I get, the most important thing is that it's locally finite. So if I pick a point, there will be only a finite number of these which touch this point. Okay? Now, definition, a smooth partition of unity of M is a collection, is a family of functions, let me call them f alpha from M to R, such that first The support, well, actually, there would be, yeah, property one is that f alpha of p is non-negative for any p. Okay, so first of all, every function must be non-negative. And then, if I take this collections of f alpha, the supports of f alpha, so this is by definition what is the closure So I want this family, remember now I didn't write alpha will vary on some families of index A. So again, this is alpha in A. So this is a locally, finite. Okay, it's a slightly, it's a very formal way to say what? That given any point, what does it mean it's locally finite? It means it for any point only a finite number of them touches. But these are the supports of the function. So how can you rephrase it? Is that for any p, there exists a finite number of alpha. So there exists alpha 1, alpha k. Now this k might depend on p, but it's finite. Okay? In A, well, for any alpha in A with alpha different from alpha 1, alpha k, p, okay, there exists a finite number such that away from those, the functions is 0, are 0. Okay. I should have left that there exists alpha 1, alpha kp. No, let me not. So there exists alpha 1, alpha kp for any such that for any alpha different from those, this is it. So this family of functions basically, imagine you have even a continuous family of these functions. So suppose that A is the set of real numbers. Okay? But for any point there are only 25 non-zero. Okay, so basically they are all 0 except a finite number, okay, for any point. Okay, this is very different from saying that they are all 0 except a finite number, because this set will change point by point. Okay, what do we do with and then actually this is still mystery, and the property 3 is exactly this. But because now I can write it, the final crucial property is that the sum for any p. So these are non-negative functions. For any, now I can phrase part 3 only after part 2, because otherwise this symbol could be meaningless. No? Because now I know that for any point there is only a finite number, so this looks like an impossible sum, in fact an undefined symbol. Okay? But I know by part 2 that this will be non-zero only for a finite number of choices. So it's a finite sum. Okay? Yeah, and actually it would have been nice to have, it's a family. Well, there is property 0. If I forgot to say that, of course, f alpha has to be smooth. Otherwise you can do whatever you want. Okay, this is a bit hard to digest, I understand, but it's quite a curious thing to, in fact, the idea of breaking the number 1, the constant function 1, into the sum of very different things. Okay. Okay, so the key theorem here is that if I take a regular covering, UI, xi, there exists a partition of unity what is called subordinated to. I want as a partition of, let me call it Fi, well, F alpha with some choice of index, where the support of F alpha is contained in UI. So that for any alpha, there exists I. Okay? So you see, I have a family of functions with these properties whose support, each of these support is contained in one of the charts. Okay? And in fact, being irregular, since I gave all these names to the balls of radius 3, balls of radius 2, I can actually construct it with a bit more. This would actually tell me that the support is contained in the ball of radius 3, but actually I can be even more precise. And the support of F alpha is contained in the ball, in the closure, in xi of the ball of radius 2. Okay. It has to be there, no? It's contained in the image of the ball of radius 3, so I can even prescribe it to be inside the closure of radius 2. Okay, so
support of F alpha is contained in xi of UI.
sorry?
Support of F alpha contained in xi of UI.
Yeah, where alpha and I are related by these conditions. So for any alpha, there is a canonical I, at least one.
I mean, support of F alpha is
Is in M,
subset
no?
of M, yes. And UI is
UI is in Rn,
yeah.
and xi of UI is in M.
Yeah, so support of F alpha should be contained in xi of UI. Like the previous.
Oh, yes, okay. Yes. Okay, let me think how do I want to convince you that this is an interesting thing. I think actually if you think of the applications, probably you realize what's really going on. So, you see, if we are trying, we play often the game of importing over a manifold something coming from Rn via the chart. Okay? This works very well locally. Now, for example, the notion of a differentiable function, then all the local notions on the manifolds were actually imported from Rn via the map X. Now the problem starts, the big problem starts when you import something a bit more globally. You want to extend from one chart to another chart something that you have done locally on one chart. So suppose that you have two charts intersecting, and in some sense here I can define, basically this part is indistinguishable from Rn because there is the map X. And here this is indistinguishable by Rn because there is a map Y. But the union of the two things, everything I construct here, it's hard to pass to the other one. Okay? So that's where the partition of unity comes in. If I could basically take a structure here and sum it. So suppose I have a machine that for any chart gives me something. We will see it in action this many times. And I want to extend it to the next chart. Okay? Now, that's where it comes. You see, you would like to take the sum of all these objects. I mean, suppose you have something, whatever it is. Phi I. So for any I, for any chart, I have an object defined over xi of ui. The point is, how do I pass it to the other one? So I start with one and I want to extend it, and I want to extend it, I want to extend it. Well, that's where the partition of unity becomes very useful, because if I have something like that, I can do something like this. While this one makes no sense. You see, and how do I imagine? So this was the ball of radius 1, actually. So of course, just to complicate things, in between there is the ball of radius 2, the image of the ball of radius 2. I'm thinking of this as something. So what does it mean? That the support is contained in the ball, in the image of the ball of radius 2. It means it's 0 out of here. So if I want to draw Fi for this specific I, I'm looking for a function which is non-negative. It's 0 everywhere. And typically, I mean, suppose actually I have a further problem. If I want to draw a picture, suppose that this point, the central point, actually belongs only to this chart. You see, it's a locally finite, so in principle it belongs to a finite number of charts. Suppose for a moment it belongs only to one. And then I have this condition here. So this is actually telling me that for this point, this function has to be 1 here. Because it's the only one non-zero. Everything, I'm assuming for a moment that there is only one. So, and then it's non-negative, so really I'm looking for, if I have to draw the graph, it's something that, so, it's 0 everywhere. I reach 2, no, which is the radius. Actually, it's 0 out of here. And then I know that at 0 is 1. I'm thinking of the radius of this ball as a function of the radius. Suppose I can do it rapidly, for example. I'm looking for a smooth function like this. Then, of course, somehow it's extended radially, so it's something like this. So this would be kind of the, if everything was radial, which is, of course, impossible, it doesn't even make sense, but that would be the meaning of the function. Now, of course, suppose I have another one, and suppose actually here I have the same drawing and the same picture. So here I have an F2, if you call it this F1, and I'm looking at F2. There might be a competition somewhere. So in this area, there could be the intersection with something else. In fact, there has to be, because otherwise this is not true. Okay? So the points belonging here, they will belong also to some other charts of this form. And there will be another function which will try to push this one up to 1. Okay? So I'm writing the function, constant function 1, as the sum of all these kind of strange things. Okay? It's kind of hard to imagine, it's difficult to intuitively imagine that you can do it.
So partition of unity gives the kind of distribution of, yeah.
Yes. Okay. I'm breaking 1. Of course, it would be better not to have 1 at one point. No, you want to keep some freedom to, by all these things, putting them together in such a way that they sum to 1.
Kind of probability.
Yeah. Okay. And the fact that you can do smoothly, it's because of the existence of the famous functions e to the minus 1 over t squared. I mean, the fact that the point is that there exists a smooth function which is 0 here, you see, which is actually the proof that at this point I won't give you. It's an exercise in calculus, and there is no geometry here. is what? Is basically convince yourself that the famous function is smooth. In fact, this theorem fails completely in the real analytic setting. Okay? Or in the holomorphic setting. There is nothing like a holomorphic partition of unity. There is nothing like a real analytic partition of unity. Because of course you are forced to use these functions which are zero everywhere, and then they become non-zero. So they violate unique continuation continuously, okay? Okay, so that's more or less the idea. I think you really have to think of these bells. Now the height of the bell depends on how many open sets will touch this point. If there is only one, you go up to 1. If there are 2, presumably you go to 1/2. Okay? And basically you actually write down them explicitly by this function here. Okay? I'll show you 2 applications of of the existence of this. And as I said, let me underline that this is a very special feature of smooth differential geometry, of smooth maps, of smooth functions. Okay? So if you want to do different type of things, this can actually break down quite dramatically. Okay?